Okay, so in this chapter, we're going to be discussing the periodic table, how to draw molecules. We'll be talking about resonance structures, Lewis structures, and basically drawing organic molecules and assigning the hybridization, which is the geometry. So first of all, we need to look at the periodic table, and in organic chemistry, I'm setting my timer here. Okay, so in organic chemistry, we're talking about really the first and second rows of the periodic table. Organic chemistry has to do with carbon-containing compounds, and you'll see that carbon likes 4 bonds, so, and 0 lone pairs. And this is, if you know that, that's going to make drawing these molecules easier. We're also going to be talking about nitrogen. Nitrogen likes 3 bonds and 1 lone pair. Oxygen typically forms 2 bonds, 2 lone pairs, just say lone pair LP, and then fluorine and chlorine and bromine iodide for those Lewis structures like 1 bond, 1 covalent bond, and 3 lone pairs. You'll want to get used to drawing these molecules fairly quickly. These molecules will be, or these elements will be typically in your reagents. We will not be spending a lot of time with those. And same thing with boron. But hydrogen always does a single bond, covalent bond. And then if you ever see lithium, sodium, magnesium, or potassium, which you will, you need to go ahead. These are going to be cations. And remember, a cation is a positive charge, and you'll want to make those a positive charge. And then the other element, which is going to be typically oxygen, will get a negative. If it's a carbon with lithium, like lithium carbon, like something like this, you'll just want to go ahead and make lithium the positive, and you'll want to make carbon the negative, which would end up being a Lewis structure like this, with carbon being negative. So let's practice this in atom. Okay, so what happens is you have electrons that first fill up the s orbital, and so when you saw hydrogen and lithium and sodium, these are all valence electrons that are in the s orbital. So the first group 1 and 2A of the periodic table, their electrons, their valence electrons are in the s orbital, which has a shape of an s sphere. The p orbitals, carbon and boron and nitrogen and oxygen and fluorine, their electrons, their valence electrons are in these p-shaped orbitals. And you remember that 2 orbitals will hold 2 electrons, and so there's a p orbital and there's a p orbital and there's a p orbital. Now what you're going to find, though, you don't have, except for like hydrogen fluorine. So hydrogen fluorine will have, to make this covalent bond, hydrogen has its 1 electron in the s orbital. Fluorine has a sideways p orbital that it puts 1 electron, and then it has, and that's the overlap. There's an overlap of orbitals here where you have the s and the p orbital. So you have a hydrogen 1s orbital overlapping with fluorine's 2s orbital, makes that covalent bond. You might see something like that. The overlap makes the bond. Now these are pure s orbitals and pure p orbitals. However, when you get into carbon, so if carbon does something like a double bond here, so you're going to draw a multiple, this is ethene. You'll learn about this. Ethene is a carbon-carbon double bond. Now what happens here is you'll count how many things are bonded to this carbon. This is a thing or a group. This is a 1, and that's, so 3 groups are bonded to carbon. So sp2. We can add these superscripts. So there's a 1 plus 2 is an sp2. So carbon is an sp2 hybridization. So in this case, it's not an s-shaped orbital or p-shaped orbital. It's a hybridization. It has about 33% S, and then it has 66% P character. So what would that be? Let's use our imagination. the S is kind of like this, and the P is like this. So now it's going to look more like a wiffle ball bat. Wiffle ball bat, if you've ever seen one of those, where you have kind of more P, but then it's still kind of an S orbital. And so that's what this has. Each one of these bonds are more like a wiffle ball shape, and then that's how the overlap in the shape is forming that carbon-carbon double bond. And that's so these are the electron probabilities. So you'll see that's Schrodinger's equation, which is quantum mechanics and electrons, where the electrons are. And this is a probability of shape. You're not going to find electron out here, out here. You're going to find it in these types of orbitals. Okay, so that's what we're showing. With the first row, we have the 1s orbital of hydrogen, and then helium, which we will not be using, fills up the s orbitals. Each orbital where an electron is found houses 2 electrons. And then these are the different shapes of the s orbital, and there's 3 types of p orbitals, the x, y, and z, and they're on the x, y, and z orbitals. But like I said, you're going to be dealing with carbon, and carbon does a hybridization. So you're going to have to be able to assign hybridization. And so to find out the valence electron, it's actually the group number. So lithium will bring 1 valence electrons. Valence electrons are the outer shell electrons that participate in the hydrogen bonding. Carbon is 4, so it will bring 4 valence electrons. You're going to see that the noble gases do not participate in bonding. And this is about the bonding. Ionic bonds, basically when you see sodium, you're just going to make that a positive because it's giving its electron. So if you see something like sodium methoxide, you're going to say, okay, well, sodium gave up its electron, oxygen took the electron. So if you did this Lewis structure here, you would do carbon likes 4 bonds, 0 lone pairs, and then oxygen will be something like this, and you'll see that that's a negative because it will assign formal charge. And I'll show you how to do that here in a minute. So that's just showing you what ionic bond is. Ionic bond is in the ion. The ions are cat ion, which if you think about a kitty cat, you might have some positive, happy feelings with the kitty cat, like Hello Kitty, right? Cat ion, that's positive. And then the anion is negative. You might think of an onion. An onion makes you want to cry, right? Tears, because onions make you tear up. That's an ion. It's a negative. So there you go, sodium. And then covalent bonding is what we're going to do about sharing. And the reason why this is important, one of your learning objectives is I can draw correct Lewis structures. And that's the most important thing you can do because you're going to have to assign functional groups. Everything in organic chemistry will start with a Lewis structure. Now, the good news about the Lewis structures are you're just dealing with basically, carbon, row 2. Okay, so they're just showing you hydrogen brings in 1 valence electrons and another valence electrons, and then they have an overlap. And this is a covalent bond. And so it's an overlap of 2s orbitals. So you could say 1s, 1 to 1s, 1. Sometimes you'll see it written like this. Okay, the second row is what we're going to be dealing with, and we're going to be dealing with like a lot of carbon. Carbon likes 4. It has 4 valence electrons, and it forms 4 bonds. So something like this, carbon forms 1. So what does this look like if carbon has its 4 valence electrons and hydrogen has 1, and there's 4 of them? Hydrogen comes in. Let's put an X there, or we'll just put in. So hydrogen comes in with its. And so hydrogen is actually an overlap of an s orbital. Hydrogen cannot do a hybridization, okay? So it comes in with its 1s electron. Now carbon, though, as you can see, has 4 and is bonded to 4 things. And so 4 things is sp3, because 3 plus 1, add the superscripts, equals 4. So 4, so that's sp3 hybridization. You'll memorize sp3. The shape of that is tetrahedral. This should be kind of review, which has a 109.5 degrees Celsius, degrees bonding separation. So what does this mean? That means 25% is S and 75% of the orbital makes up P. So it's going to have a little bit of S, a little bit of P, and it's going to be hybridized. And so this is what carbon for each one of these is going to come in with some kind of sp hybridized shape here where the electrons are. And then hydrogen is going to come in with its unhybridized s orbital, and that's how you get these this overlap makes up the covalent bonds. So here we look at the number of bonds. So hydrogen has one bond and has one valence electron. Carbon likes 4 and lone pairs. The reason why you want to know these and kind of memorize these is because this is going to help you quickly realize whether you have to assign. This is going to help you determine whether you need to assign formal charge. So if any of these deviate from this, hydrogen cannot deviate, fluorine cannot deviate. So these will not deviate, fluorine will not deviate. But oxygen, nitrogen, and carbon can deviate from these number of bonds and lone pairs. So kind of look at a periodic table and see that's 4, 3, 2, 1, and then that's how many lone pairs, 0, 1, 2, 3. And if they're ever anything different, then you're going to need to assign formal charge. So the important thing is to be able to quickly draw Lewis structures. Every second row has to complete the octet rule. So you cannot have any more than 8 electrons. Hydrogen always has 2 electrons for its octet because it can't have any more. A solid line indicates a 2 electron bond. Okay, so carbon's going to be pretty much in the middle. I always think of it like a choo-choo train. And then for something like this, if you see hydrogen after the carbon, those hydrogens all bond to that carbon, and chlorine also bonds to that carbon. Carbon likes 4 bonds, so it's going to be something like this. These all bond to carbon, okay? Hydrogen can never be in the center, okay? So because it cannot form 2 bonds. Here, something like this, since carbon can, and you won't see stuff like this, you would see me write this as CH3NH2, okay? And what that would mean is these 3 hydrogens bond to that carbon, these 2 hydrogens bond to that nitrogen, nitrogen bonds to that carbon. So here we have the 3 hydrogens, and then we have, so carbon has 4 bonds, 0 lone pairs. Nitrogen then has 2, and then it has a lone pair. Nitrogen likes 3 covalent bonds, we'll just say bonds, covalent bonds, and 1 lone pair. And so you want to draw these with the least formal charge. So if you can get 0, that's great. They have to follow the octet rule. So here hydrogen has 2 electrons each. Now if you do this old school, you total up your valence electrons. So it's the total number for the group number. Okay, so group number for carbon is 4, hydrogen is 1, and there's 5 of them, and then nitrogen is 5. So what is that? That's 5 and 10. That's 14 valence electrons. And if you count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you're only allowed 14 electrons in this whole molecule. And then you have to make sure that they all have the complete octet. Remember, hydrogen only needs 2. So each one of these hydrogens are okay. Carbon has 8. 1, 2, 3, 4, 5, 6, 7, 8. nitrogen has to have 8. 1, 2, 3, 4, 5, 6, 7, 8. So those are good. And if you follow the bonding pattern, where carbon has 4 bonds, 0 lone pair, and then you have nitrogen with 3 bonds, 1 lone pair, then you don't have to worry about formal charge. And that's what this is telling you. Assign formal charge to all atoms. So you only have to do that if you have to assign a formal charge. If there's no formal charge, then don't worry about it. So here, when you do a multiple bond here, see, so carbon has, so if you saw something like this, CH2, CH2, this is called a condensed formula. And if you do your POGIL, you'll learn that. So the condensed formula, if we want to draw a Lewis structure, we have to show all of our bonds. So here, these hydrogens are bonded to that carbon. And then these hydrogens are bonded to that carbon, but that carbon's bonded to that carbon. Okay. Now, you can add up your total valence electrons here. Carbon has 4, hydrogen 1, there's 2, and then you got another carbon 4, and then 2. That is 8 plus, or 6 plus 6 is 12. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can do 11, 12. And then the thing is, we don't want that. We want carbon to have 4 bonds, 0 lone pairs. So we're going to convert that lone pair into a double bond. So this is a multiple bond. We keep everything else the same. Now, when you do that, you have the same number. And then you want to check the octet. Hydrogen has 2. That's good. Each carbon has 1, 2, 3, 4, 5, 6, 7, 8. So that's good. Now, to check the formal charge, you might want to memorize this. This is formal charge equals group number, GN, for group number, minus dots, minus dashes. Okay, dots are electrons, and dashes are just the bonds. So carbon would be in group 4, and there's 0 dots on this carbon. So look at this carbon, minus the dashes, 1, 2, 3, 4. So 4 minus 0 minus 4 is 0. So it has a formal charge of 0. Okay, so here's a question, and let's work this. Draw the Lewis structure for HCOH. So now, how is this going to be? Can we draw it like this? Well, you want to figure out the connectivity. This is how I would draw it. Because let's talk about our total valence electrons. So our count is 1 plus 4 plus 6 plus 1. Where am I getting these numbers? From their group numbers on the periodic table. Hydrogen is in group 1, carbon is in group 4A, oxygen is 6, and hydrogen's 1. So that is 5 plus 7 is 12. And so, go ahead and start learning the functional groups. Functional groups aren't until next week or chapter 3. But go ahead, this class is going to be fast and furious, so go ahead and learn the functional groups, and you'll learn that a lot of these have to do a functional group. Now here, the connectivity is to put carbon in the middle, and also POGIL will help you do this as well. Okay, so then we connect these, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here we have our 12 valence electrons, we have our connectivity. And the problem with this is carbon only has 1, 2, 3, 4, 5, 6 valence electrons. That is not an octet. Okay, so then we can take this pair and make a multiple bond. So if we do that, we want to redraw. So we redraw with carbon double bonded to oxygen, and we still have the same number of valence electrons. And this, you'll learn, this is an aldehyde. It's actually formaldehyde, which preserves bodies. And this has, carbon has its 4 bonds and 0 lone pairs. And oxygen here has 2 bonds and 2 lone pairs. So 2 bonds, 2 lone pairs for oxygen. And then for carbon, we have 4 bonds, 0 lone pair. And I know that the formal charge, when it follows this bonding pattern, is going to be 0. But let's just see. Formal charge for oxygen. Well, the group number of oxygen is 6, minus dashes, minus dots. Well, it has 2 dashes, and it has 1, 2, 3, 4 dots. So what's 6 minus 2 minus 4? 0. And you can do the same thing for carbon here. Group number 4 minus dashes is 4, and dots is 0. And so draw the Lewis structure. How many covalent bonds are in the structure? So when you get the correct Lewis structure, which is always going to be the one with the least number of formal charges on your atoms, 1, 2, 3, 4. The answer is 4. Okay, now let's draw the structure for this compound. Well, the connectivity is these hydrogens go onto the carbon, and the carbons are connected to the carbons like a choo-choo train, okay? And then the carbon is connected to oxygen. And when you learn your, what do you call that? The functional groups, I'll say FG, then you'll kind of know that these hydrogens are on this nitrogen, and you'll know that you want to have something that resembles a functional group. Okay, well, I'm going to redo this. I don't know why I can't erase it. So, sorry. We're going to do this again. So, and this will be a double bonded oxygen, and what I'm doing is I'm doing let's do our bonding patterns. So hydrogen only has 1, and all these hydrogens are bonded to that carbon, and the carbon's also bonded to that carbon. So, and then the carbon has 4. And then here, the tricky thing is oxygen is bonded to the carbon, and oxygen likes 2 covalent bonds and 2 lone pairs. So I'm just going to go ahead and put the lone pairs on oxygen. Carbon likes 4 bonds, and so 1, 2, 3, 4, and hydrogen likes just 1. And see how these hydrogens precede the nitrogen? So that is there. And then what does nitrogen like? It likes 3 bonds, 1 lone pair. So we're going to put a lone pair there. Now let's just add up our total valence electrons here. Okay, so when you do that, what do you have? Total valence electrons. Carbon has 4, hydrogen has 1, there's 3 of those, 4 plus 6 plus 5 plus 2, so 10 and 17 plus 7 is 24. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so we do have the 24. Does everything complete its octet? Yes. The oxygen has 8, nitrogen has 8. You cannot have more than 8. How many lone pairs are there in this structure? So you would say 1, 2, 3. There's 3 lone pairs. Okay, this is what it's saying. Formal charge equals, and I just do group number minus dashes minus dots. And this is what your book says for that formula. I like mine better, but you can do what you need. Okay, so they're showing you if carbon has 4, then this is its preferred bonding. Here, carbon shares, but it has 4, and here, 1, 2, 3, 4, 5, 6, 7, 8 it has an octet. But what is the formal charge here? Well, carbon is group 4. It has 3 dashes minus 2 dots. So that would be 1 minus 2 is a negative 1. So in this case, it's a negative. And so they're showing you when you get the formal charge, if you do anything other than this bonding pattern, you need to, alarm should be going off in your head that you need to assign a formal charge on that element. Okay, so like here you can see the nitrogen, what's the formal charge equals the group number 5 minus dashes, 2 minus dots is 4. So 5 minus 2, 3 minus 4, that's a negative 1. Here, you take like oxygen. If you put oxygen with 3 bonds, formal charge for this oxygen would be group number 6 minus 3 dashes minus 2 lone pairs. That's 3 minus 2 equals 1. That's a positive 1 charge. What is the formal charge on the indicated oxygen? Okay, well, what is the formal charge equals group number minus dots minus dashes. And now that's different than what I did before. It doesn't matter. Okay, so group number is 6, dots 1, 2, 3, 4, 5, 6, minus dashes is 1. So did you get 6 minus 6 minus 1 is a negative 1. Okay. So let's do another. Okay, so this oxygen is, formal charge is group number 6 minus how many dots? 2 minus dashes, 1, 2, and when you're not seeing this is 3. So 6 minus 2 is 4, 4 minus 3 is positive 1. So that's a positive 1. So these are exceptions to the octet rule. The one that you're going to see some and when we get into reagents is boron. Boron has an incomplete octet, so it can have six electrons, 1, 2, 3, 4, 5, 6. It cannot not exceed none of the elements can exceed 8 electrons in the second row. Okay, so elements in the third row can have more, and you'll see this in phosphorus a lot, and maybe some sulfur, because they have, in the third row, they have d orbitals. And d orbitals, even if they don't use them, they can put electrons in them. The group 2, row 2, does not have any d orbitals, so they cannot exceed the octet. Okay, isomers. Isomers are compounds that have the same molecular formula, but different connectivity. And you'll hear me say that a lot when I'm working through problems. Same molecular formula. So always, if you're working these, always figure out what the molecular formula is. The molecular formula is this, when you have the little numbers, okay? So these all have the same molecular formula. That means they're related. They're related somehow. These two compounds are related because they have the same molecular formula. One of your learning objectives is I can classify the relationship between molecules. And these are going to build. You're going to keep building on this concept. And the first thing you want to do is always figure out the molecular formula. So see, you have C2, and then you have the hydrogens next, 1, 2, 3, 4, 5, 6. There's 6 of those and 1 oxygen. Here you have C2, you have 6 hydrogens, and you have 1 oxygen. These have the same molecular formula. That means they're related. Okay, but their connectivity is different. This you're going to learn when you learn functional groups, and the sooner you learn functional groups, the easier this activity is going to be. You'll see that this is an alcohol, okay, because of this OH makes it an alcohol. Ethanol is the active ingredient in beer. Okay, this is dimethyl ether. So this is a carbon, oxygen, carbon. Okay, that carbon makes it an ether. So these are different functional groups. They're different compounds, but you would say that they're going to be isomers. You wouldn't say that they're not related. They are related. They have the same molecular formula, but they have different connectivity, so they are isomers. Okay, so I'm going to keep going. We're doing 2 days lecture in one. Okay, so now resonance is a concept where they're the same. Even though they're different, as we see it, they're the same. So if you're looking at a television, and the television box is like this, or the television box is like this, and you draw it, it's still the TV that you're looking at. They're just different representations, but they're the same thing. That's kind of what a resonance is. A resonance, they're two Lewis structures. They have the placement of the atoms, but they have a different arrangement of electrons. And so therefore we use a double-headed arrow to say these are the same thing. So when you're drawing resonance structures, you're going to see that you're going to take these two electrons there, and you're going to draw these curved arrows, and that means these two electrons now go to form a pi bond. And then these electrons go to form a lone pair. So the pi bond goes to form a lone pair, and then here the lone pair goes to form a pi bond. I will post an activity that I think is really good for how to draw these curved arrows for the resonance structures. But just so you know, resonance are the same, resonance hybrid. These electrons are delocalized, and a compound has more stability if it's resonance stabilized. And the way you would draw such resonance structures to go from one to the other is these are called curved arrows. And this is when you have this negative, you start with the negative charge, the formal charge, and you go from a lone pair to a pi bond, and then you're going to go from a pi bond to a lone pair. And in this paper that I posted, they call this a type 1 and a type 2 arrow, because you have to push those electrons. Otherwise, if you didn't, because these are electron pushing arrows, when you read your book, these electron pushing arrows, if you just stopped with one, then carbon would have 10 electrons, which would exceed the octet rule. And so to go the other way, these would go from oxygen lone pair to a pi bond, and then the pi bond onto nitrogen, pi to a lone pair. And when it goes to a lone pair, the formal charge changes. Notice also that the overall formal charge on this compound is negative, and overall is negative, so formal charge is conserved. Resonance structures aren't real. They're not in equilibrium. Equilibrium is what we'll be talking about the next chapter. Equilibrium arrows are forward and backward. A resonance structure is a double-headed arrow. And they're not isomers. Isomers have arrangements of the atoms. So like the hydrogens or the oxygens or the carbons are going to be connected differently. Okay, so that is an isomer. These are not isomers. These are just the movements of electrons. So rule number 1, two resonance, they can differ in their multiple bonds or non-bonded electrons. So that's what we were just talking about. Here it's the electrons, and they can go from a lone pair to a double bond, and then they can go from a double bond to a lone pair. This is not right, because if you don't push those electrons here onto oxygen, then you exceed the octet because here you have carbon. Carbon has 10 electrons, which exceeds the octet. Okay, so in that paper that I also put on there for resonance structures, there's a thing called the type 3 arrow, and these are in cations. So cations are your positive containing compounds, and as you can see, that carbon, now this one's fine, the carbon only has six electrons, right? On this, there's only 6, but that doesn't exceed the octet, so that's okay. And you see how these electrons, this is in that paper is a type 3 arrow that goes, and now it exchanges places because now this carbon has the positive charge. Notice that this overall has a positive, this overall has a positive. Here this is a negative, so we need type 1 and type 2 arrows. And so that's how you would draw those curved arrow notations that you are responsible to do. Okay, you can have an atom with fewer than 8 electrons, but it can never have more, So that's what we're showing you here. See, this carbon here has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It actually has 12 because this denotes a lone pair there. Well, 10. But anyway, it's wrong, you see. So here, when you have electrons here, this is okay, but this is not ideal. I mean, you see that the -1 and the +1 cancel out to 0. And then here, this one has formal charge overall of 0. But every element has a formal charge of 0. So this is going to be a thing we call a major contributor. So this is your major contributor. You're going to have like 4 reasons why you would assign one structure as a major contributor, and then which ones are minor contributors. A major contributor is going to have the least number of formal charges. So here we have the position of the double bond changes. So here, these electrons can go here, but then those go there, and they're showing you that. Okay, so let's work this one together. Give you a moment. Resonance structures. Okay, so how many acceptable resonance structures can be drawn from the following? And so here's one. So this is resonance structures number 1. And then we're going to push those electrons here. And then we push those electrons there. And we're going to draw that structure. And then when they go there, there's where the negative charge goes. And you can check your formal charge on that. And then, so that's resonance structure number 2. And then we can draw another resonance structure where we do a type 1, type 2 arrow again. All of the actual elements need to stay in the same place. You do not move them. The only thing that changes is the movement of lone pairs and pi bonds. And now oxygen has a formal charge of negative. So the negatives overall conserved. And so we have 3. 3 is the answer. Now, which one are the major contributors? The major contributors, they all have only one formal charge, which is negative, but the major contributor will be this one and resonance structure number 3, and you'll learn that's because the negative charge needs to be on the more electronegative element. And so electronegativity increases up a group and over. Oxygen is more electronegative than carbon. So it's going to want the negative charge. And that's what we're talking about, major contributors versus minor contributors. Better resonance structures will have more bonds and fewer charges. So here we have 1, 2, 3, 4, 5, 6, 7 bonds. Here we have 3, 4, 5, 6 bonds. And of course you have the two different charges here. Here, this one's going to be your major contributor because oxygen is more electronegative than nitrogen. Okay, so how many acceptable resonance structures can be drawn for the following? You always want to draw in your lone pairs that are not shown. And I expect you to do that, so I drew those. And then you're going to always want to start with the negative. So the negative will push those electrons, and that will go like so. And then this gets a positive, and this is a negative if you sign that. You also have these electrons here. They can go here. And so when you draw that, you get something that looks like this. That's a positive and positive. Now, what you'll see is this is an overall charge of 0. This is overall charge of 0. This is overall charge of 0. Okay, now this is going to be a minor contributor because we're going to have less bonds, and more charges. These are going to be equal because the negative charge is on the oxygen here and the negative charge is on the oxygen. So I would say there's 3 acceptable resonance structures for this, and these are your major contributors right here. We have 2 majors, and this would be a minor contributor. So here, this element, this is a CH3. Okay, so carbon has 3 hydrogens there. That would be sp3. That cannot participate in resonance. This one, if you draw in your hydrogens, which I recommend you do, you'll see that that's sp2. Oxygen here, 1, 2, sp2. What is this hybridization? Well, you count things. 1, 2, 3, 4. So you might want to call that sp3, but if the next door neighbor, your next door element, is an sp2 and you have lone pairs, then it's going to be sp2 because it can participate in resonance, and resonance always wins. Another thing before we go on is the only elements that can participate in resonance are your sp2 and sp. You have to have an unhybridized p orbital to participate in resonance. So let's go back here. Okay, they're just showing you the bond length. I'm not too concerned about that, but there's some bond length information. This is very important. If you have 2 groups, like so, then you would say, okay, there's 2 things bonded to the carbon. That's going to be linear, 180-degree bond angles. 3 groups, that would be something like this. Oxygen has 1, 2, 3 groups, so that's sp2, and that's trigonal planar. That means everything's 120 degrees. This is Vesper. Carbon, here's sp2. And that means that these 2 elements can participate in resonance. And that's what they're showing you here. Also here, ethylene is a ripening agent, by the way. So you can spray that on like your green tomatoes, and then they will ripen. Bananas give off ethylene. There's my banana. Okay, and the 4 groups is tetrahedral. We don't have a square thing, so tetrahedral is 109.5 degrees. And these sp3 do not participate in resonance. So no resonance for sp3 elements. Sometimes that's important because you don't know where to go with your resonance structures. solid line. Oh, so whenever, you only do this for SP3 elements. This wedge means it's in front, going towards you. These are in the plane of a piece of paper. So if you put a piece of paper out there, this would be the plane. The wedge means it's going in front of the paper, and then the dash means it's behind this piece of paper. Okay, so that's the dash and it's behind. You do that for SP3 compounds, elements. And you always want to draw these on the same side. So whether you draw this like this, you want to have your wedge and your dash on the same sides of each other. What you never want to do is this, okay? So, and I will call you out on that. This is very wrong, 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 okay? So you got to have them on the same side of the paper, of the carbon. Nitrogen, this is an sp3, and because that would be 1, 2, 3 things, and so this is your plane, and this would be the wedge coming at you, and this is your dash going behind. A water molecule, so if this is bent, and so you have sp3 with the electron geometry, but this is a bent geometry because those lone pairs will push those molecules down. sp3 means it's going to be less than 109.5 degrees because the degree of angles is based on your electron geometry. So here's some examples, and this should be reviewed. Okay, so what's the hybridization of nitrogen? 1, 2, 3. So sp2, because you add your superscripts. Okay, so there's three things, three groups onto nitrogen. 1, 2, 3. So you add your superscripts. That's sp3. sp3 is always going to be trigonal planar. Okay, so hybridization, sp3 is trigonal planar if you asked for geometry. sp2 is trigonal planar. sp3 is tetrahedral. You can just memorize that. That's 109.5. Trigonal planar is 120 degrees. And then sp is linear. The nice thing is these are the only ones you really need. So sp3. sp2, sp2, sp2. Oh, I'm sorry. Okay, and then what is the bond angles for an sp2? You have to memorize that. It's going to be 120. All right, so this is your condensed structures. This is your POGL. And I am not going to lecture on this. I am going to tell you to work your POGL activity, POGL activity number 1. There is an accompanying video that shows you how to draw molecules in the different forms. You'll see that there's Lewis structure, condensed, and line structures. This is very important that you take the time to work this POGL. This is also, it kind of teaches you that this is kind of incorporated between them, but that hydrogen belongs to that carbon. This CH3, because it has a parentheses, is branched. The OH is in the end here. You'll learn that this is an alcohol. You need to start looking at your functional groups. This is an alkene because you got a carbon-carbon double bond. This is an alkane. This oxygen here, this is an ether because the oxygen's bonded to 2 carbons. So you need to be able to go, you'll find that this is condensed, and then this is a Lewis structure. Most of the time I will be drawing structures in the line drawing, the line angle drawing. I don't do my condensed with even a line such as that. And like I said, You'll need to kind of work your POGL for these. You need to be able to see that that's an aldehyde. You want to be able to quickly do this. You'll want to see that this is a ketone. You'll want to see that this is a carboxylic acid. You'll want to see that this is an ester. And these are the condensed formula. You want to be able to quickly be able to draw them back and forth. This is your kind of your condensed Lewis structure versus your condensed structure. This is the skeletal structure, and so each one of these carbons, every point is a carbon, and then every carbon has 4 bonds. So like this carbon already has 2, so that means it has 2 hydrogens. This carbon has 1, so that means it has 3 hydrogens. So you want to be able to go back and forth from these Lewis structures to skeletal structures. If you have them in a ring there, you'll see that each one of these carbons, since they have 4 bonds, what's not shown here is the hydrogens. Okay, so hydrogens are not shown in a line structure, a skeletal structure. You want to practice being able to convert from these skeletal structures to Lewis structures. If you have a nitrogen, you do those they're called heteroatoms. And heteroatoms are atoms other than carbon or hydrogen. So heteroatoms that you're typically going to see are nitrogen and oxygen. You want to draw those hydrogens in. If you see a carbocation, then you want to draw that hydrogen in and show that there's only 1 hydrogen there. If it's a negative, I would like to see the lone pair. And that means the carbon only has 1 hydrogen. So, this is going to be very important for problem solving. Okay, so if you have a formal charge, you need to be able to put that in there. So you see that oxygen here has a formal charge. So that would be only 1 lone pair on oxygen. Excuse me. And so this one has no lone pairs. So you want to be able to draw out those lone pairs. This is just for shape. Oh, this is the hybridization we were talking about, the hybridized orbital. Like I said, just take nitrogen, count the things, and then keep in mind a lone pair is a thing, equals a thing. So here we have 1, 2, 3, 4, so sp3, and you add the superscripts. We've talked about this. So I won't spend the time doing this. Oh, this is important. So for single bonds, you have bond rotation. So they're constantly going and rotating. When you have a double bond, you don't have rotation. There's no rotation around a double bond. And what does that mean? You're going to find that means it has a top and a bottom. A top and a bottom. And then we're going to see that this is in the name, since it can't rotate. These are sp2s. They're 120 degrees because there's 3 things, right? Carbon has 3 things, so it's sp2. 2 plus 1 is 3. There's no rotation around the double bond. So it will matter. This red is oxygen, blue is nitrogen. If you get one of those molecular model kits, which might help you in Chapter 5, and functional groups, you can do that, and you can use those on your exams if you need to make molecules and such. I think they're probably $20 to buy. So this is a triple bond, no rotation here. It's so this is an alkyne, and because carbon's only bonded to 2 things, it's sp, and that's 180 degrees, and it's linear. Okay, so here is a table summary of what we've been talking about. Okay, so what is my question on this slide? Let's see what my question might be. Let's see. Which of the following is the condensed formula is correct? So the question is, which condensed formula is correct? So hopefully you did CH3, go here, and then you come here, and you can say CH, and then you can go here, and you say CH, and then you can go to the next one, CH2, and then you can go to this last one here and say CO2H. And so which one does that match? Let's see, there's your CH3, there's your CH, there's your CH, there's your CH2, but this one's missing the H here. So let's go to the next one, CH3, CH, CH, CH2, and then CO2H. So C is the answer. Okay, so how are these compounds related? Which of the following condensed formula is correct? Okay, so which one? Oh, that's not the question. The next, how are they related? Okay, so how are these two related? You might want to convert them to line structures. So I just start with this here because those are branched. So this would be CH3, CH3, CH3. This is where the POGL is going to help you. You got to get good at this. Here's your CH2. Here's your next CH2. And then this is CO. So we're going to double bond that O there, and that's CH2. This is CH. There's your Br. And then you have CH, and then CH2, CH2. Now, you also want to do the molecular formula. Remember I told you to do that first? So it's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many hydrogens? Molecular formula, MF. 3, 6, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and then we have one oxygen and one Br. And so we can do that here, but I'll go ahead and convert these. CH3, there's your CH, and then we go to the next one, CH. Okay, well that's a CH, and that's a CH. That's going to be a double bond, CH to CH, and then that's a CH. Might even want to put those H's in there. So that's an H, because 1, 2, 3, 4, and then this one, 4, and then a CHOH. CH2. Okay. I wonder if there's a typo in this because thinking that there's too many CH's here. But anyway, it's still a good problem to work. So there's that OH there, and then this CH2 here, and then let's go to this CH with the Br, and then that CH with the 2. Okay, so I think that, where is it in enol? See, this C has 4, and this CH, so there's carbon, CH, CH, and then this CH. Okay, so I think that's right. Well, anyway, so let's just see first how many carbons and see if they're even related, because this means not related means not same molecular formula. Okay, so we got to see that first. So we got 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Is that right? 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Here we have 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's 18. All right, so I made a mistake there, folks. Okay, how many hydrogens? 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 22, 23. And then we have 1 oxygen and 1 bromine. So they're obviously related because, as you can see, they have this same molecular formula. But you see how the connectivities are different? This is a ketone. This is a functional group. This has an alcohol. So I'm going to say that these are constitutional isomers because they have the same molecular formula but different connectivity. Okay, now here, short and strong. Short and strong. Short and strong. So the triple bond is going to be shorter, see, and it's going to be stronger. Okay, so this is short and strong. And so short, this one's going to be your alkane. Like I said, I don't worry about that so much, but I do just memorize that the short and strong are your triple bonds, so they're going to be shorter and they're also going to be stronger. So just remember short and strong. And this, we've talked about this, hybridization. We'll have SP, you got to make that 100%, 50% S character. SP2 is 33% S character. And the more S character, so the SP would be an alkyne. You're learning these. Once you learn the functional groups, it's easier. SP3 example would be an alkane. And to be fair, you would want to do carbon-carbon bonds if you're doing the comparison. So this, it would be more less S character. This one would be a double bond, and that's an alkene. What is the hybridization of oxygen in the following structure? So you'd want to convert this to a Lewis structure here. So you have CH3, you have 2 of those, and then you have this CH here. So this is this carbon. So you see CH3, CH3, and this is your CH, and then you have another CH, and then you have another CH. This has got to be a double bond here. And then you can draw your H's in there. So if you wanted to draw this H, if you wanted to draw this H, and you want to draw that H, and then this is a CHO, which I know is an aldehyde. Okay, so here we have that. Now, what is the hybridization of the oxygen? So you got to draw in. Oxygen has 2 bonds plus 2 lone pairs. So I drew in the lone, and so it has 1, 2, 3 things. 3 things. So that's sp2. You got to, the superscripts need to add 2, 3. So sp2. And you should know sp2 is bond angles of 120 degrees, and it is trigonal planar, which means it's flat like a piece of paper, planar. Electronegativity, increasing electronegativity goes up a group and over. So you need to know oxygen is more electronegative than nitrogen. And what does it mean? In a bond between carbon, like an oxygen, it's going to be like pulling those electrons towards itself. So you're going to show the dipole of oxygen pulling those electrons towards itself. We don't memorize these numbers. This is just considered nonpolar because the electronegativity difference, which I'll call is E and delta, electronegativity difference is so small that it's considered nonpolar. Where you get polar bonds are when you have heteroatoms like oxygen and nitrogen. So once again, when you learn the functional groups, you can also be able to characterize things like that. So oxygen, here we draw this like this. Those electrons in that bond are going to get pulled towards the oxygen and make it a polar bond. And that's going to determine a lot of the physical properties. And it's also going to determine the chemical reactivity that we're going to be learning for the rest of the summer or the school year. And this shows you the shift of electronegativity, in this case going towards the chlorine, because the chlorine is more electronegative than carbon. And so this makes, when you have an electronegativity difference, you have a polar molecule. So overall, this is your net dipole for the molecule, because these vectors add. So when you push the electrons towards oxygen on both sides, overall, if you add these in physics, you would learn that they would go north for the molecule. Here you have symmetry. Whenever you have symmetry, those dipoles will cancel out, and they cancel out equally. So you'd sometimes see that as the dipole, which is like a funky U, and D means debye, which is a unit. So it has 0 debye, which means 0 dipole. So they're showing you water has a dipole with electron density going towards the north. And here the overall molecule, since it has symmetry, it's going to have 0 D. This would be polar, so it's greater than 0 D. D for debye. Okay, so this one once again kind of got cut off. So I will see what the question says. Which of the following would be the most polar? Okay, so you draw the Lewis structures out, and you'll see that this is nonpolar. It's an alkane, and it has symmetry. The bromine, if you drew these out, you would see that the tetrahedral would be nonpolar. And here, when you draw these in tetrahedral, you could do this is a wedge and this is a dash, because they're tetrahedral sp3. This one here, you have a ketone. So this ketone makes, this is actually acetone if you work in the lab, and the dipole goes towards the north. So this would be greater than 0 debye. This would be a polar molecule. And then C6H6 you would see is benzene. And you see that that is a hydrocarbon. That's what we call them, a hydrocarbon. When you start learning functional groups, that means there's only hydrogen and carbon present. So that's going to be a nonpolar. There's no oxygen or nitrogen. There's no heteroatom. So whenever you have no heteroatom, you can call that a nonpolar molecule. You have a heteroatom, you need to draw it out, and you can see that that's going to be polar. Here we have alkenes, and you'll learn to draw that. This has symmetry. So this goes here, and this goes here, and that is 0 D. This is nonpolar. Because it has symmetry, you'll see that this is called a trans. We're going to learn the language of naming. Here, this pushes towards the fluorine because fluorine is more electronegative than carbon. And so the overall dipole here is this. You'll see that when fluorine's on the same side, such as this is a cis molecule. So how are these related? You'll see that they have the same molecular formula. They have different connectivity. So these are isomers. And these isomers are cis and trans. And one of them is nonpolar. And then one of them is polar. So compound B has a dipole moment. Okay, and this one is to do a resonance structure that is a positive. So it has actually 2 hydrogens on there. You might want to draw that in there. And then this would be resonance structure number 1. And then these electrons can go there. And then you would want to redraw this. And you'll see that now the positive is there. These are that type 3 arrow. So this is resonance structure number 2. And they're pushing those electrons towards the positive. Now we do not put anything here or here, because if you drew these hydrogens in, you would see these are sp3 carbons, sp3. sp3 cannot participate in resonance. Okay, so that is 3 resonance structures. And that completes this, chapter 1.